So for the better part of this week, we've talked about a couple of different core concepts. One of the biggest ones that we talked about is the idea of enthalpy. Enthalpy is just a measure of how much energy is either going into a reaction or coming out of a reaction. So enthalpy just measures energy. And as it measures energy, it also measures energy movement, again, whether it goes into a reaction or it comes out of a reaction. When it goes into a reaction, we call that endothermic. That should draw back things from like Unit 2. So again, when it's endothermic, energy is going into a reaction. On the flip side, when energy comes out of a reaction, we call that exothermic. So we've got this major idea of enthalpy. And we see that it really just measures whether energy is going into a reaction, whether it's coming out, whether energy is required, or whether we're going to get something back out after the reaction is run. Enthalpy also has the characteristic variable of delta H. So that's that triangle and H. So there's our variable for enthalpy. One of the biggest other ways we can determine whether something is going to be endothermic or exothermic is based on the sign of delta H. So if delta H is positive, we know that it requires energy, so it's endothermic. Energy has to go into it. However, if delta H is negative, we know that energy is coming out of that reaction. We know it's exothermic. So again, all that enthalpy does is it measures energy. So it also comes with the variable kilojoules. Kilojoules is something that we've seen before. It was that Q value from like Unit 2, where we're looking at calculating the heat going into a piece of metal or coming out of a piece of metal. How is energy transferred? It's all about this enthalpy value, this delta H value. So now we look at this delta H and we see, well, how can I use this to help me calculate something in a reaction? How can I determine whether I'm going to be getting a bunch of energy out or whether I'm going to need a bunch of energy to make sure this reaction happens? So a lot of times when we're given a reaction, the delta H value is something either given in the problem or something listed next to our problem. So in the case of a problem like this, where we're talking about the hand warmers that are normally typically found in cold winter stores or in sports stores, it follows a basic reaction. It's where iron reacts with oxygen gas and actually forms iron 3 oxide. And it actually releases a great deal of energy just from this general idea. So we actually see that our delta H value in this case is about 1,652 kilojoules. So that's a lot of energy for such a simple reaction as iron just being exposed to the air. We're also going to make sure that our reaction is balanced though, because it's going to help us when we start generalizing this enthalpy value to different things within our problem. So there you go, now it's balanced. These coefficients become particularly important because when we want to start generalizing this enthalpy value to different things in the problem, we have to look at that coefficient first because it tells us a great deal of information. In this particular case, it tells us that for every 4 moles of iron that we get, we're going to end up getting out 1,652 kilojoules of energy. In another sense, we could say for every 3 moles of oxygen gas, we're going to get out this much energy. Or for every 2 moles of iron 3 oxide produced, we'll get this much energy out. So it becomes a conversion factor for us. It lets us solve a great deal of different kinds of problems based on a simple premise that there's energy coming out of this reaction. But if we want to write it as a conversion factor, sometimes it's more helpful to look at it like this, where we're saying, well, for every 4 moles of iron, we're going to be getting out 1,652 kilojoules of energy. This lets us use a much broader unit conversion factor. It lets us do a much more dimensional analysis, which is a lot of what enthalpy calculations boil down to. It's just how do we use this idea to generalize it to different sorts of problems. The second big concept that we covered over the last couple of days is this idea of entropy. So entropy measures the randomness of a system or how much chaos is going on. So again, it measures chaotic nature or randomness. It comes with the characteristic variable of delta S. Delta S is how we measure that entropy value. So the higher our entropy rating, the more chaotic our system is, or the more random things appear. We have two ways to determine whether entropy is increasing in a reaction or decreasing in a reaction. So if we have matter being dispersed into multiple different things, so if I have something, let's say, ammonia breaking down into nitrogen gas and hydrogen gas, in this case, matter is being dispersed. We have one thing in the beginning, it's being broken apart into two separate things. We would say that entropy is increasing. It's becoming more chaotic. In this sense, it's becoming much tougher to keep track of these two objects as opposed to this single object. So in this case, delta S is increasing. The other way we can see if delta S is increasing or decreasing has to do with the temperature. So as temperature increases, the speed of our molecules also increases. So as temperature goes up, speed also goes up. And as the speed goes up, we can see that different things also occur. The faster things are moving, the tougher it is to keep track of those things. So again, as delta T goes up, delta S also goes up. So the warmer something is, the quicker it's moving, the harder it is to keep track of it. So again, entropy is increasing as temperature increases. Another way to think about this is as states change. So a solid is a very well-ordered structure. As we begin to heat it up, it becomes a liquid, which is tougher to keep track of, and then a gas, which is really tough to keep track of. So as our object continues to heat up, that entropy value, or that randomness, continues to increase as that temperature increases. So the last thing that we talked about is how do we put enthalpy and entropy together in order to help judge whether a reaction is going to occur by itself or whether we need to be putting energy into it to make sure that that is continuing to progress as it should. So again, we're looking at how delta H and delta S are kind of work together to determine spontaneity. Now for us in chemistry, spontaneous has a little bit different meaning. So if a reaction is spontaneous, we would say that it continues to occur without intervention. So again, spontaneous means that the reaction will occur without intervention. That means once we get it started, it's just going to kind of continue on until eventually it stops because it runs out of fuel or runs out of one of the components that's in that reaction. So how do we use delta H and delta S to determine this? So again, it's much easier for energy to be coming out of a reaction than it is to be going into a reaction. So exothermic tends to be much more likely than endothermic. So if delta H has a negative value, if it's an exothermic reaction and delta S is increasing, which is also a natural tendency, in that situation, that reaction would be spontaneous. Because it fulfills both of our conditions, both that energy is coming out and that randomness or that chaotic nature is also increasing. Both are normal conditions that apply to most everyday life situations. On the flip side, if we have to be putting energy into a reaction, if we have to continue to pump energy in, and it's entailing that your delta S is decreasing, your entropy value is decreasing, in that case it would be not spontaneous. Because we have to pump energy in and it's going opposite of how things tend to work. Most things tend to move towards chaos. They tend to get much more chaotic or much more random as time moves on. However, if we get things that are decreasing in entropy or decreasing in that random character, that's very much the opposite of how things tend to work. So we know those two for sure. The places where kind of strange things happen is where we have delta H being negative, which is good, which is advantageous for us. However, delta S is decreasing. So half of this makes sense where, yeah, energy should come out of most reactions. However, our randomness is decreasing. It's getting smaller. So in this case, well, we're not sure if that's spontaneous or not. It very well could be, or it couldn't be. It really just becomes temperature dependent. What's the temperature that this is occurring at? We're also not sure what happens if delta H is positive, so we have to put energy in, and delta S is increasing. So again, we have half of that situation, which is very advantageous, which makes a lot of sense, where delta S, or the chaotic nature of something, is going up. But we have to put energy in to make that happen. So again, it becomes something that's temperature dependent. It very well could be random at very specific temperatures. However, at other temperatures, it might not be spontaneous. So this is how we use enthalpy and entropy in order to judge spontaneity.